In lesson 8.3 we have three goals. The first is to use the integral test to determine if a series is convergent. The second is the comparison test, again to decide if a series is convergent, a sum of terms. And third, error estimate if we are approximating the sum of a series. We'll begin with a memory refresher. In lesson 5.10 we dealt with improper integrals type 1, and an example was 1 over x squared from 1 to infinity. The approach is to replace infinity with t and take the limit as t goes to infinity. So we begin by writing the limit as t heads toward infinity from 1 up to t for 1 over x dx. The x squared is in the denominator. The antiderivative would be x to the negative 2 becomes x to the negative 1 divided by a negative 1, in other words, negative 1 over x. With that thought in mind, we have the antiderivative as negative 1 over x, and then we have to do the substitutions for 1 up to t. And we still haven't done the limit, so we're rewriting the limit every time as t goes to infinity. Substitute the t in there, we get negative 1 over t. Put a minus sign down, substitute the 1, we get a negative negative, so we get a plus 1 over 1. And of course, this does go to 0, and it does converge to 1. So the infinite area from 1 to infinity for 1 over x squared, this is type 1's, does converge and has an area of 1. We'll also be looking at type 1's with other powers. For example, 1 over the square root of x from 1 to infinity. And if you recall, we generalized and gave a rule in lesson 5.10. And if we were integrating from 1 to infinity for 1 over x to a power p, if p was bigger than 1, the area converged, we were able to get a limit. And if p was less than or equal to 1, it diverged. Again, memory refresher, we will be using those today. The first series that we're going to look at is the series 1 over n squared as n goes from 1 to infinity. And if we expand out a few terms, it's 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, and so on. So the question is, does this series converge or not? And what we can do is compare that to the function 1 over x squared. If we look at the graph for 1 over x squared, of course it drops and is heading towards 0. If we graph each of these as if they were a rectangle, a width of 1, in this case the first one has a height of 1, the width of 1, and the height would be 1 over 2 squared, so this represents its height, and again a width of 1 and 1 over 3 squared, and so on. It should be clear that the area of the rectangles represents the series, and the total area of the rectangles is in fact representing the sum of the series. We can easily see that the rectangles are below it, so if 1 over x squared converges, then the series would also converge. So in effect we are doing a comparison. If we're trying to decide if this converges or not, we can compare it to the series, or the integral 1 over x squared from 1 to infinity. Now, it does actually only go from 1 to infinity, so excludes the first rectangle. But that's a finite space anyway. It's 1 over 1 squared. And then the rest of the area would be smaller than the curve. And since we know that this approaches 1, it's true that that must approach 2. And since the integral converges, it's true then that the series must also converge since it's below it and must be smaller than 2. So it's true that this series has to be smaller than 2. Another common one would be that 1 over square root. And if we are trying to decide what does this series do, 1 over the square root of n, as n goes from 1 to infinity, yes, we would again compare it to the function 1 over square root of x and its area from 1 to infinity. Again, examining the graph, 1 over the square root of x does decrease. This time, if we expand the terms, the regions of the rectangles are above the curve, each having a width of 1 and a height which represents each of the terms. And since we know that this is divergent and it's smaller than the actual area underneath the rectangles, it's true then that this series must also diverge. So in effect, we are doing a comparison when we are doing that integral. The integral test does say that the function we use must be continuous, positive, and decreasing. It doesn't have to be decreasing immediately, but eventually it must decrease. So let's walk through one more example.